Good day, students, and welcome to our video tutorial and intervention in math. Now, let's explore and learn another lesson of general mathematics. We are now on the week 3 of our module, the module 9 entitled Intercepts, Zeros, and Asymptotes of Rational Functions. In the previous lesson, you learned how to find domain and range of a rational function. In this particular lesson, determining intercepts, zeros, and asymptotes of rational functions will be done. Our learning objectives. After going through this module, you are expected to: number 1, recall the meaning of intercepts, zeros, and asymptotes. Number 2, identify the intercepts, zeros, and asymptotes of rational functions. Number 3, solve for the intercepts, zeros, and asymptotes of rational functions. Intercepts and zeros of rational functions. The intercepts of the graph of rational functions are the points of intersection of its graph and axis. The y-intercepts of the graph of rational function r of x, if it exists, occur at r of 0, provided that r of x is defined at x is equal to 0. To find y-intercept, simply evaluate the function at x is equal to 0. So meaning, your y-intercept is the value of y when your x is equal to 0. So in our figure, we have the point 0 and 3. So the value of your y there is 3. So the y-intercept is 3. Next, the x-intercept. The x-intercept of the graph of the rational function r of x, if it exists, occurs at the zeros of numerator that are not zeros of the denominators. To find x-intercept, equate the function to 0, meaning your x-intercept is the value of your x when the functions becomes 0, or meaning the value of your x when y is equal to 0. So in the figure, as you can see, your x there is 2 and the y of course is 0. And of course, the zeros of a function are the values of x which make the function 0. The numbered zeros are also the x-intercepts of the graph of the function, meaning if you want to find the zeros of the function, of course, you have to get, of course, the x-intercept of the function. Now, let's try with the example. For number 1, find the x and y intercepts of the rational function f of x is equal to 3 minus x over x plus 1. To find the x-intercept, equate the function to 0. So for example, this function f of x is equal to 3 minus x over x plus 1. So equate the function to 0 by replacing the f of x or your y to 0. And then solve for x. Then by symmetric property of equality, so you are going to interchange the values both in each side. using the symmetric property of equality. And then multiply both sides by x plus 1. So in our previous lesson in solving rational function, we have to find the LCD. And the LCD of this equation is x plus 1. So you have to multiply both sides in x plus 1. And we have 3 minus x is equal to 0. Then, by the addition property of equality, so we have to add negative 3 to eliminate the 3 values in there. So each side of the equation, this equation, will be added negative 3. So 3 plus negative 3 minus x is equal to 0 plus negative 3. So 3 plus negative 3 is equal to 0. Then 0 plus negative 3 is negative 3. So we have negative x is equal to negative 3. Since we are going to find the negative the value of your x, but there the value of x is negative, so we have to simplify. So to simplify this one, we have to multiply each side by negative 1 using the multiplication property of equality. So negative 1 times negative x becomes positive x. And negative 3 times negative 1 is positive 3. So our value of x now is x is equal to 3. So the x-intercept is in the point of 3 and 0. So this is the ordered pair. So take note, in the ordered pair, the first value there is our x coordinate. Then the second one is the y coordinate. So since we are going to find the x-intercept, so the x value there is 3, and of course the y is 0. Then to locate this one, or to graph this function, so our x-intercept there is this point, 3 and 0. So by analyzing the example, we can say that to find the x-intercept, simply equate the numerator of the function to 0. So in our next activity there, so we are going to equate this numerator to 0 in order to find the x-intercept. Next, so another, to find the y-intercept, change the x value of the function to 0. So meaning you have to replace or evaluate the value of your x to 0. All the value of your x. So substitute 0 to x values of the function. So meaning the x value there will be replaced by 0. So f of x is equal to 3 minus 0 over 0 plus 1. Then simplifying the fraction. So we have 3 over 1. Then 3 over 1, of course, is equal to 3. So the y-intercept of this function is 3, or in the point of 0 and 3. If we try to plot this one in the graph, so our y-intercept is in this point, 0 and 3. So our x there is 0 and the value of y is 3. To recall, our x-intercept is the value of your x-intercept is the value of your x when y is equal to 0. And the value of y-intercept is the value of your y when x is equal to 0. Another example. To find the x and y intercepts of the rational function f of x is equal to x squared minus 3x plus 2 over x squared minus 4. So simply equate the numerator to 0 to find the x. So first, let's find the x-intercept. So in getting the x-intercept, just simply equate the numerator of the function to 0. Now we have x squared minus 3x plus 2 is equal to 0. So our equation now is in the quadratic form. So in the quadratic form, we have to find the x value by factoring. So we have the factor of x minus 2, a quantity of x minus 2 times quantity x minus 1 equals 0. Then the value of your x, to solve the value of your x, so using the zero product property, each of the factor will equate to 0. So x minus 2 equals 0, then x minus 1 equals 0. Then we have the value of x. We have two values of x. The x is equal to 2 and x is equal to 1. So the x-intercepts are 2 and 1. But by looking at the denominator of the original functions, if we substitute 2 to the value of your x, then the value becomes 0, meaning your function becomes undefined. So the denominator will become 0. So undefined yung rational function natin. So the function becomes meaningless. So we will only accept x-intercept. So this is only our x-intercept, because when we try to use this 2 in our rational function, the function becomes undefined. So the x-intercept of this function is x equal to 1, or the intercept at x equal to 1 or in a point 1 and 0. To plot in the graph, so this is our x-intercept. Next, to find also the y-intercept of this function, so change the x value of the function to 0. So meaning you have to substitute all the x values of this function to 0. So 0 squared minus 3, and I got minus 3 times 0 plus 2 over 0 squared minus 4. So 0 squared is 0, then 3 times 0 is 0. So 0 minus 0 is only positive 2 over negative 4. So positive 2 over negative 4. Then reduce the function to lowest term. We have negative 1/2. So this is the value of our function, or the f of x, or our y. So the y-intercept is negative 1/2, or in a point on the ordered pair 0 and negative 1/2. So in graph, so this is our y-intercept there. So the x-intercept is 1 and 0 in point 1 and 0, and the y-intercept is in a point 0 and negative 1 half. Now let's try another. For now, we have to determine the zeros of the following rational functions. For letter A, j of x is equal to x minus 2 over x plus 6. For letter B, h of x is equal to x minus 3 over x squared minus 9. To find the zeros of the rational function, equate the function to 0, or simply solve for the x-intercept of the function by equating the numerator to 0. So for problem A, g of x is equal to x minus 2 over x plus 6. So equate the numerator, which is our numerator is x minus 2. So equate the numerator to 0. So this is our numerator, x minus 2. So x minus 2 equals 0. Then solve for x. Our x is equal to 2. Thus, the zeros of g of x is 2. So this is our zeros of the function. Next, for problem B, okay, h of x is equal to x minus 3 over x squared minus 9. So to simplify this one, so by factoring the denominator, as you can see, the rational function there is factorable, and of course it will be simplified. The denominator there is x squared minus 9. So we have to factor. So the factor of x squared minus 9 is quantity x minus 3 times quantity x plus 3. Then they have the common factor in the numerator and denominator. So we have to divide the common factor, which is x minus 3. And it will become 1. So the numerator there becomes 1 over x plus 3 equals 0. So we have to equate the numerator to 0. Then 1 is equal to 0. This is the false statement. If we try to analyze, 1 is equal 0 is not possible. So meaning there is no zero of the function, which means that no point on the graph touches the x-axis. So in the graph, you have to find that there is no graph touches the x-axis. Now let's proceed to another lesson, asymptotes. So what is asymptotes? Asymptotes is an imaginary line to which a graph gets closer and closer as the x or y increases or decreases its value without limit. And of course, we have kinds of asymptote. First, the vertical asymptote, horizontal asymptote, and oblique or slant asymptote. Vertical asymptote, the vertical line x is equal to a, so this is our vertical asymptote, is a vertical asymptote of a function f if the graph increases or decreases without bound as the x values approach to our a from the right or left. So this is our illustration. By looking at the illustration, we can see that the graph of the function is approaching at x is equal to negative 5, represented by the dotted line. And as we can see, the graph is getting closer and closer to x is equal to negative 1. But it will not pass or intersect to the line. So the vertical asymptote of the graph is at x is equal to negative 5. We can find the vertical asymptote even without looking at the graph of the function. So meaning, the value of this vertical asymptote x is equal to negative 5 in our example, this is also not a part of your domain. That will make the functions undefined. This is the value of your x when that makes the function undefined. As simple as that. Then, to find the vertical asymptote, so first determine the vertical asymptote of a rational function. So first reduce the given function to the simplest form, and then find the zeros of the denominator that are not zeros of the numerator. Meaning, you have to find the value of x that makes your denominator 0, but it will not make your numerator zeros because it will no longer the vertical asymptote. It will become the zeros of the function. So you have to carefully determine the vertical asymptote. So examples, determine the vertical asymptote of each rational function. For problem A, f of x is equal to x minus 1 over x plus 5. For the solution of problem A, the zero of the numerator is 1 and the zero of the denominator is negative 5. So the vertical asymptote for f of x, so simply equate your denominator to x to 0. So x plus 5 equals 0. Then we have the value of x is equal to negative 5. So the value is 0 of the denominator but not for the numerator. So if we try to negative 5 to our denominator, it will not become 0. But for our denominator, it will become 0. So the vertical asymptote of our function for the problem A, x equal to negative 5. For problem B, f of x is equal to x plus 2 all over quantity x plus 1 times quantity x minus 4. So the zeros of the numerator is negative 2. So we have to equate this one to 0. So negative 2. And the zeros of the denominator are negative 1 and 4 because each of the factor will equate to 0. So your value of your x is negative 1 and 4. the vertical asymptote for f of x plus 2 all over quantity x plus 1 times quantity x minus 4r, x is equal to negative 1 and x is equal to 4. So we have two vertical asymptotes of this function. So these values are zeros of denominator but not of the numerator rather. Then for problem C, j of x is equal to 2x squared minus x plus 1 all over x squared minus 6x plus 9. So our solution there, since the function is in the quadratic form, so reduce it into simplest form. So the simplest form of g of x, 2x squared minus x minus 1 over x squared minus 5x plus 6 is j of x, quantity of 2x plus 1 times x minus 1, quantity x minus 1 all over quantity x minus 3 times x minus 2. So the zeros of the numerator are negative 1 half and 1. And the zeros of the denominator are 3 and 2. Since we have to equate each of the factor of your denominator. So the vertical asymptote for g of x of this function are x is equal to 2 and x is equal to 3. These values are zeros of denominator but not of the numerator. So correction there, numerator. Next, what is horizontal asymptote? So the horizontal asymptote line y is equal to b. So is a horizontal asymptote of the function f if the f of x gets closer to b as x increases or decreases without bound. So our vertical, rather the horizontal asymptote there is in this broken line, horizontal asymptote. So we have also the horizontal line. Looking at the graph, we can see that the graph of the function is approaching to a line in the y-axis. That line is called, of course, the horizontal asymptote. In the graph, we can see that it's getting closer and closer to y is equal to 1. So the graph there is closer to our horizontal asymptote. We can determine the horizontal asymptote arithmetically by comparing the degree of the leading coefficient of the numerator and denominator of the function. So to find the horizontal asymptote, so determine the horizontal asymptote of a rational function. So first, we have to compare the degree of the numerator denoted as n. So this is the degree of the numerator n, and the degree of the denominator denoted as d. Take note, the degree of our numerator is n and the degree of our denominator is d. So there are three scenarios to find the horizontal asymptote. So first scenario, if n is less than d, automatically our horizontal asymptote is y is equal to 0. Like for example, f of x is equal to 2x squared plus 3 over 2x cubed plus 5. So the degree of the numerator there is second degree since the highest exponent is 2. So the degree of numerator is 2 and the degree of the denominator is the third degree since our exponent is 3. Meaning, the degree of numerator is less than the degree of our denominator. So, as you can see, 2 is less than 3. So, automatic, your y value or the y is equal to 0. So, the horizontal asymptote is y is equal to 0. How about if the degree of the numerator and denominator are equal? So, meaning, if n is equal to d, the horizontal asymptote of y is the ratio of the leading coefficient of the numerator a to the leading coefficient of the denominator b. That is y is equal to a over b. Sorry for this formula. So, correction, y is equal to a over b. Y is equal to a over b. Ayan. So, y is equal to a over b. So, like for example, if we have the function 6x squared plus 4 over 2x squared plus 6. So, as you can see, both of the degree of numerator and denominator is in the second degree. So, we have the highest exponent, which is 2. So, they are the same. So, simply divide the leading coefficient of the numerator and the leading coefficient of denominator. So, the leading coefficient of your numerator is 6. Then, the leading coefficient of your denominator is 2. So, simply divide their leading coefficient. So, y is equal to 6 over 2. Then, simplify. Sure, your y there is equal to 3. And this is our horizontal asymptote. Another example, another scenario, how about if the degree of your numerator is greater than the degree of the denominator? So, there is no horizontal asymptote of this function. Example, f of x is equal to x squared plus 3 over x plus 10. So, the degree of your numerator there is in the second degree. Then, first degree yung denominator. So, the degree of numerator is greater than the degree of your denominator. As you can see, the exponent is 2, while the exponent of your denominator or the exponent of your denominator is 1. So, automatic, the value of your f of x, or the value of the horizontal asymptote is null, or there is no horizontal asymptote. And take note, a rational function may or may not cross its horizontal asymptote. If the function does not cross the horizontal asymptote y is equal to b, then b is not a part, of course, the range of the rational function. Example in determining horizontal asymptote of each rational function. For problem A, f of x is equal to 3x plus 8 over x squared plus 1. For the solution of problem A, so the degree of the numerator 3x plus 8 is less than the degree of the denominator x squared. So as you observe, the degree is in the first degree, then your denominator is in the second degree. So the degree of the numerator is less than the degree of the denominator. So our horizontal asymptote is y is equal to 0. How about for the function f of x? We have 3, f of x is equal to 3 plus 8x squared over x squared plus 1. So as you observe, the degree of the numerator is the same with the degree of your denominator because the highest exponent there is 2. So they are the same. So the degree of the numerator 3 plus 8x squared and that of the denominator x squared plus 1 are equal. Therefore, the horizontal asymptote of y is equal to the ratio of the leading coefficient of the numerator, which is 8, to the leading coefficient of your denominator, which is 1. There. So 8 over 1 is equal to 8. So our horizontal asymptote there is in the point y is equal to 8. For problem 3, j of x is equal to 8x cubed minus 1 over 1 minus x squared. So the degree of numerator 8x cubed minus 1 is greater than the degree of the denominator 1 over x squared. Therefore, there is no horizontal asymptote. So, aside from vertical and horizontal asymptote, a rational function can have another asymptote called oblique or slant. It occurs when there is no horizontal asymptote or when the degree of the numerator is greater than the degree of the denominator. So, since the problem C there it has no horizontal asymptote, so meaning this function has of course the oblique or slant asymptote. So what is slant and oblique asymptote? An oblique asymptote is a line that is neither vertical nor horizontal. It occurs when the numerator of f of x has a degree that is one higher than a degree of the denominator, or meaning if we have no horizontal asymptote or the function has no horizontal asymptote. Okay, looking at the graph, we can see that there is a vertical asymptote. Of course, we have the vertical asymptote and there is no horizontal asymptote. In this case, the oblique or the slant asymptote using your knowledge of division of polynomials. So, simply dividing the function. To find the slant asymptote, simply divide the numerator by the denominator or by either using long division or synthetic division. So the oblique asymptote is the quotient with the remainder ignored and set equal to y. So if there is a remainder, then you have to ignore the remainder and the answer or the quotient there is simply equate to y. Consider the function h of x is equal to x squared plus 3 over x minus 1. Determine the asymptotes. So first, by looking at the function, so find the vertical asymptote, equate the denominator to x, the x minus 1 equals to 0, then we have x is equal to 1. So the vertical asymptote of h of x is at the line x is equal to 1. And of course, there is no horizontal asymptote because the degree of numerator is greater than the degree of the denominator. So, we have to find the oblique asymptote of this function by dividing numerator to from the denominator. So, we have to divide x squared plus 3 over x minus 1. So, if the numerator and denominator h of x are divided, so we get, so using the long division or synthetic division, we have the quotient of x plus 1 plus 4 over x minus 1. So, our 4x minus 1 there is the remainder. So, just ignore the remainder. And the value x plus 1 will be equate to y. So, the line y is equal to x plus 1 is the oblique asymptote of h of x is equal to x squared plus 3 over x minus 1. So, I think you're ready for the next module. So, that's the end of our video tutorial in this module, which is module 9. So, I think you are ready for the next module, module 10, in solving real-life problems involving rational functions, equations, and inequalities. So, hoping you have some learnings about this. You understand about this module before we proceed to the next module or the next video. So God bless and thank you.